ME347, Example 4. Calculate streamlines, pressure field, acceleration, and vorticity for a specified velocity field. A two-dimensional velocity field for an inviscid flow is given that has velocity components in the x and y directions. The acceleration due to gravity is indicated to act in the negative z direction. The pressure is P0 at the origin. For part A, show that the flow behaves like an incompressible fluid. For part B, obtain an expression for the pressure field. For part C, find the streamline that goes through x equals 1 meter and y equals 1 meter. For part D, solve for the fluid acceleration and the vorticity fields. To solve this problem, we are assuming that the flow is two-dimensional and inviscid as stated in the problem statement. For part A, to demonstrate incompressible flow behavior, we need to show that the velocity field satisfies the incompressible form of conservation of mass for Cartesian coordinates. Substituting in the x and y components of velocity, we indeed get that 0 equals 0. For part B, we want to obtain an expression for the pressure field. Since we already know the velocity field, we can use the differential form of the momentum balance equations to find the pressure field. Note that this differential form of the momentum equation is commonly referred to as the Navier-Stokes equations, and it represents Newton's second law applied to an element of fluid in a differential control volume. Thus, the mass per unit volume times the fluid particle acceleration is equal to the sum of the forces due to gravity, pressure, and friction, all per unit volume. For this problem, where the flow is being modeled as inviscid, the net force due to friction is neglected, resulting in a form of the equation commonly referred to as the Euler equations. These equations are both vector equations written in vector notation. Thus, they each have three components. First, we write the x component of the Euler equations. Many of the terms are zero, and the equation reduces to a much simpler partial differential equation that can be integrated as shown. Note that for the partial derivative, instead of just a constant of integration, we get a possible function of y and/or z. Second, we write the y component of the Euler equations. Again, many of the terms are zero, and the result of the integration is shown. Note that this time we include a possible function of x and/or z. Finally, we write the z component of the Euler equations. Again, many of the terms are zero, and the result of the integration is shown to be just a hydrostatic variation with a possible function of x and/or y included. Combining our results for all three components and using the pressure specified at the origin, we get our final pressure distribution. For part C, to find the streamline through x and y equal to 1 meter, we must first solve for the stream function for our known velocity field. First, we get a solution based on u, which is the x component of velocity, and then we get a solution based on v, which is the y component of velocity. Again, because these are partial derivatives, instead of a constant, they have an added function of x and y, respectively. Comparing our two solutions, we get a final solution. Finally, we substitute in our values for x and y to get our particular streamline. For part D, to find the acceleration field, we substitute our known velocity field into the definition of acceleration for a fluid for Cartesian coordinates in just the x and y directions for our two-dimensional velocity field. Note that the fluid acceleration includes the local acceleration, which changes with time, and the convective acceleration. For our steady flow, the local acceleration is 0. However, because the velocity is changing with location, the convective acceleration is not 0. Also for part D, to find the vorticity, which is defined as twice the rate of fluid rotation, we substitute our known velocity field into the definition for vorticity for Cartesian coordinates. Note that for two-dimensional flow in the xy plane, it is only possible to have rotation about the z-axis. In addition, for this case where the flow is inviscid, we show that the rotation for the z-axis is also 0, thus the flow is irrotational. Finally, to visualize this flow, I have plotted the streamlines with velocity vectors and the pressure field using a program in MATLAB that is available from my webpage. This case is similar to a jet of fluid that is wide in the z direction, moving towards a wall in the negative y direction towards the origin, and splitting off in the positive and negative x directions. The point at the origin is the forward stagnation point, and it has the highest pressure.